This is a series of videos showing how analytics can be used to disrupt traditional telecommunication operators' processes. Today's video is Topology Independent Automatic Network Alarm Correlation using Associative Analysis. Let's see the problem. With the communication networks becomes increasingly large and complex, issue resolution has become a very complex task. The transition to NFV and SDN networks will make this problem even worse. Fault management systems capabilities must be improved to face this increasing complexity of today and tomorrow communication networks. A telecommunication network consists of a number of interconnected components like switches, transmission equipment, routers, RNC, etc. Each component in its turn contains several subcomponents. Any of these components can produce network events and alarms. Network events are messages describing some sort of abnormal situations. They do not necessarily indicate that there has been a problem in the network that is visible to the users. The number of produced alarms varies greatly, and they are in various type. This means that a single fault can manifest itself as multiple alarms, as can have several symptoms, can be propagated, and it can have long duration. A single fault can generate directly or indirectly dozens, even hundreds of other redundant alarms. Network and service fault management systems use networks, events, and alarms to determine the nature and severity of the fault and provide a root cause analysis to drive the fault resolution. From a logical point of view, a fault management system is a sort of big funnel which collects network events, filters the events which are alarms, and groups/correlate alarms by common fault cause, and lastly prioritize the fault resolution. Historically, to solve problem of processing huge volume of alarms, alarm correlation techniques have been used. These techniques reduce the numbers of alarms by grouping alarm referring to the same fault. Alarm correlation techniques are generally graphs based on the network and services topology, alarm hierarchy, and alarm causality. Unfortunately, these techniques are extremely sensitive to network configuration changes. For example, frequent network topology changes, like the one happen in NFV networks, have big impact on the efficiency of these techniques. Some of these techniques are also sensitive to the order which alarm occur. As network elements can buffer alarms, the alarm sequence received can be different from the real sequence. Last but not least, these techniques lack in automation in the discovery of new rules. To avoid the limits of the traditional alarm correlation techniques, we need techniques that are capable to automatically discover new rules and that are independent by network topology and alarm sequence. Machine learning technique, and in particular the association analysis, can be the right solution. Association analysis allows to automatically discover association among elements using a pure statistical approach, so they don't need network topology information or the right event sequence to correlate network alarms. Let's see how the solution works. Step 1. Alarms are collected from the network or from historical data. Step 2. The network alarms are grouped by temporal windows and passed to the association engine. Step 3. These groups are analyzed to identify association rule or patterns. An association rule describes a situation like, when an event A occurs in a group, then also the event B occurs in that group. This means that association rule are alarm correlation rules, as they describe what alarms occur when a specific alarm happen. To improve the efficiency of the analytical alarm correlation engine, we need to add to the model some additional analysis, such alarm clustering. It is used to improve the alarm grouping. Decision trees, they are used to improve the rule selection. Production KPI analysis, it is used to verify the efficiency of the model.